Happy Monday, everyone. I hope your weekend went well. Hope you got to enjoy some good time with the family in your quarantined state. That you were able to connect with some people that were not virtual like this. We enjoyed some good time together. It was actually a pretty memorable Easter for us, and just thankful that we're able to really make it special, even though we're kind of in these uncertain times. And it just made us all the more grateful for the hope that we have, and the fact that that we do not fear in the same way that all those that do not have the hope of Christ do. So we have a confident hope, we have a sure hope, and it was just good to kind of reflect on that together. So you no doubt have noticed at this point that I sent out that partner project. And again, this is in lieu of the third exam. One thing that is greatly underestimated in a first pass through probability theory is how needful it is to understand how sums work. Sums of random variables specifically. So I wanted to give you a project that forced you to think through that carefully. Okay, nothing that I gave you was hard. Okay, it's all fairly straightforward, but it does involve one of the more technical, computationally heavy situations that you can encounter. Turns out that a lot of the other sums of independent random variables of the same distribution, we call those IID random variables. A lot of those work out fairly nicely, even the normal distribution. But for whatever reason, the uniform distribution gets a little technical. And I wanted you to think through that carefully. Again, not hard, all stuff that you should be able to handle, especially because you're going to be able to think along with a partner in this. So I'm hoping that it won't be too arduous. I recommend that you maybe divide and conquer, split things up and work on work on one problem a day or something like that, or, two each, and then come back together and see if you agree or disagree or what, what's going on. I just want you to have to work through that together. I know that mathematics itself, if it becomes too isolated of a discipline, that's a recipe for disaster. So I think it's a good thing for you to work in partners on this, upload a partner project. And again, in the peer evaluation, I hope it's clear what I'm saying. You're supposed to rate yourself out of 5 points, and you're supposed to rate your partner out of 5 points, but I want all of that to be above board. So I want you to discuss that amongst yourselves. And I mean, rating someone that you know, a friend even, is just part of life. It happens a lot once you get into a career. So we just get over that and be willing to do it. Talk directly with truth to one another, with grace, of course, as well. But just be honest with one another, and hopefully, there won't be any wild surprises that happen when it comes time to evaluate one another. And you probably noticed that there is a bonus question where if you do it perfectly, okay, and it's all or nothing, no in between. If you do it perfectly, it will be enough in my eyes for you to not have to take the final exam. That doesn't mean it's a hard question. You should be able to do it just by extending what you do in the other parts, if indeed you understood what was happening. But it's a little bit of a test. So not hard, but just still a little bit of a test. So I mean, just to let you know, I wrote it all down on one page right here. So it's not like it's really hard, but you have to look at it the right way, and then it all kind of works out. Especially the hints I gave you on the other parts are all kind of a similar direction you would go in that bonus question. So this one page that I wrote right here is everything for the bonus question. Okay, so just so you're aware. Okay, I liked this the way the project's laid out, just because it forces you to remember a lot of things simultaneously. So I think it works well that way. Okay, so work on that in partners. You could choose your partner. Please ask questions, reach out if something's unclear, or if you feel like something is just going wildly awry on a problem. In most cases, I think in all the questions, I probably gave you an out, like I told you to prove what the formula was, so that you're not like flapping in the breeze trying to figure out, well, I can't even move on because I don't have the formula. So hopefully the way I've structured the thing makes sense and is helpful to keep you moving along well. Okay? All right. So I am going to pick and choose a few topics out of chapter 7 just to cover. I mentioned that I have been doing things in chapter 7 as we've been moving along. Whenever we hit on a topic that I feel like really connects to something that happened to be treated in chapter 7, I've gone ahead and used it. For instance, when I did the stuff with the hypergeometric random variable, and even with the binomial, and really all the stuff I've been doing with like moment generating functions, a lot of that stuff isn't really treated in full detail until this chapter. But there are a few things that I want to point out and make sure that you really have solidly down, okay? And one of those things is the value of writing a random variable as a sum, okay? Being able to analyze a sum of random variables is really the bread and butter of probability theory. And it really is the thing that moves us from just kind of highbrow theoretical stuff to really practical things in the context of statistics. So being really good at being able to realize that, hey, this is just a sum of random variables. It's a very useful tool indeed. So I want to spend some time talking about that. How can I think of this random variable I'm looking at as a sum, and to have some intuition in terms of how to do that, okay? So there's no better way to start than with the so-called union bound. Okay, at some point I proved the union bound, you remember? So the union bound said the following. The union bound, sometimes called Boole's inequality. Okay, Boole's inequality, it said this. Okay, so A1 ... AN were events. And really this thing didn't need to stop necessarily, okay? We could have gone on forever. Then the probability of the union of these things, okay? So union I going from 1 to n of AI is less than or equal to the sum I going from 1 to n, the probability of AI. Okay, and we actually proved that at some point. In fact, we proved it for, we proved it for an infinite sequence of events. Okay, so let me just remark that this is also true for n equal to infinity, even. Okay, so. You could have an infinite union, and that thing will be bounded above by the sum of those probabilities in question. Okay. Sometimes this is a worthless bound. Sometimes it's very, very useful indeed. And it's really not that surprising, because if you think about it, okay, I'm computing the probability of a union of a bunch of events. That's going to involve tons of intersections. So adding together all of the individual probabilities will probably hugely overcount a bunch of overlap. Okay, so it's not really all that surprising. But here's what I wanted to do was first do an alternative proof that brings sums to bear. So here's an alternative proof involving sums of random variables. Okay. So there's these things called indicator variables, and we've talked about them before, but they're extremely useful. And if you're willing to kind of think outside the box and write a random variable as a sum of indicators, you'd be surprised how often it will take a grotesquely complicated problem and make it quite simple. Okay, so that's what we're going to do here. So let, oops, what am I writing here? Not lex, let xi be the indicator of event AI, i.e., okay, just to be explicit about what that means, xi is going to be 1 if what? If AI happens, and 0 otherwise. Okay, sometimes, let me just say that sometimes we actually write, okay, sometimes it's better to write 1 of AI, okay, for this indicator. Okay, in fact, that's probably the industry standard, so to speak, but this book doesn't tend to do that. So I don't want to necessarily lead you astray. Okay, so we have all of these indicator variables. So let's let x be x1 plus x2 plus ... plus xn. Again, if I was going to use the standard notation, this would just be, x would be 1 sub a1 plus 1 sub a2. Again, I like the 1 notation. I know that I already said that, but the 1 notation is nice because it says, that in my mind, I think it's 1 if AI happens and it's 0 otherwise. That's it, okay? Sometimes the Greek letter chi is used also for the indicator variable sometimes, but we're just using the x's here, okay? It is what it is, okay? So what is x? If x is the sum of these indicator variables, then all x is it's the number of the events that occurred, okay? Then x is equal to the number of events AI that occur. Okay. Indeed, if the x's are all 0, if the xi's are all 0, that means none of them happened. Okay. Right? If x is equal to 1, that means that exactly one of the xi's is equal to 1, and the others are 0, and that means that exactly one event happened. Yeah. Okay, etc. So this thing is literally counting the number of events, that have happened. Okay, so also let y equal to, okay, so I'm going to use my newfangled or my standard notation. Y is just going to be the indicator of the event x greater than or equal to 1. Okay. Okay, so it's the indicator of the event that x is bigger than or equal to 1. So what is y? Well, y is equal to 1 if greater than or equal to 1 event occurs and 0 otherwise, okay? Now, is it clear to you that x is always greater than or equal to y, okay? So note the following. X is greater than or equal to y. Why is that so? Well, if x is greater than, okay, so let's just kind of write this down. This is because on the event x greater than or equal to 1, we have x is greater than or equal to 1, and if we're on that event, that means that y is actually equal to 1. So x is equal to or greater than that, okay? And on the complement of this event, so x equal to or greater than 1 complement, y is equal to 0. And of course, that's always less than or equal to x. So whether we're on the event or its complement, y is never more than x, okay? So if x is equal to or greater than y always, these are random variables. If x is greater than or equal to y always, then what does that tell you about their expected values? Right, well, so since x is greater than or equal to y, remember x is x is the number of events a1 through an that actually happen, and y is simply 1 if at least one event happens, okay? Okay, so let's see here. Since this is true, we have the expected value of x is equal to or greater than the expected value of y, okay? But what's true about the expected value of x, by the way? So this is going to be the all-important situation right here, okay? But what? But the expected value of x is just the sum of these expected values of the indicators, okay? And by the way, the book doesn't do this, but I'm just going to mention again, I didn't have to stop at some finite moment or something like that. This could have been an infinite sum, right? Okay. And what can you say about these expectations of like x1, for instance? Well, I can actually compute these things, right? The expected value of x1, x1 was the indicator of the event a1. So that thing is equal to 1 with probability. So let me just say, let me kind of write this in red. This is equal to, well, it's equal to 0 times the probability of A1 complement plus 1 times the probability of A1, okay? Because there are only two possible values, either 0 or 1. So plus, okay, and then what is this? Look, notice that the 0 part, that's going to always just go away, and you're just going to end up with the probability of the corresponding event to this indicator. So it's going to be plus the probability of AN. Okay, so what do we end up getting here in the end? Look, expected value of x. It's just the sum of the probabilities. Okay, it's the sum of the probabilities. But on the other hand, what's going on with the random variable y? Okay, well, let's think about this. So on the other hand, what's going on with the expected value of y? Okay, expected value of y is equal to 1 times the probability that x is greater than or equal to 1. Okay, because that y was the indicator of that event. Yeah, So when is x equal to or greater than 1? Well, that means that one of the events, A1 through AN, happened. It means A1 happened, or A2 happened, or A3 happened, or etc. Okay? So this is equal to the probability, think about it. This is equal to the probability of the union I going from 1 to N of AI, right? That was what all that OR business was about above, okay? Thus, since the expected value of X is greater than or equal to the expected value of Y, we obtain the result that we wanted, namely that the sum I going from 1 to N, probability of AI, is equal to or greater than the probability of the union. Okay? And there's Boole's identity in all of its glory right there. Okay, so this was an alternative proof to the one that we had before by way of indicator variables. Just being willing to kind of go out on a limb, write a random variable as a sum, and just kind of look at what's going on. And by the way, I mean, if you look carefully at this proof, you'll notice that there was nothing special about, there was nothing special about there being a finite number of events here. Okay, so we could have had an infinite sum and an infinite union, and we would have been fine. Okay, all right. So there's a couple of other random variables that benefit greatly from looking at them as a sum. And I've done this a little bit before, but I kind of want to do it again now, just to make sure that it's deeply entrenched in our cognitions, okay? And just to also remind you of some distributions we've looked at in the past. So here's another example. So another sum example. Okay. So let X be distributed as binomial with N trials and proportion of success P. Okay. Okay. We know a lot of stuff about this random variable. We know its moment generating function, and therefore we know its mean and its variance. But perhaps there was some easier way to deal with this thing. Okay, and indeed there is, and it happens when we are willing and able to go out on a limb and actually write this thing as a sum. Okay, so it is possible to write X as a sum of indicators. Okay. And as a matter of fact, I should mention that in that last example with Boole's inequality, I didn't assume anything about the events. I didn't assume the events were independent or anything. I just said they were events. Okay. But it turns out that here the indicators are actually going to be independent. Okay. And we'll see why here in just a minute. So what would be the most natural indicators to use here? Remember, X was equal to, right? So X is equal to the number of successes in trials. So there's a natural way to write this thing as a sum of indicators. Namely, remember the N trials, these were the Bernoulli trials. Okay, and those Bernoulli trials are themselves, remember Bernoulli trials are either like 0 or 1 with probability P, okay? And the thing is, those were really just indicator variables in the end, okay? So it makes sense that what we would do here is we would write X as a sum of N indicators, where Xi is simply going to be the indicator that the ith execution of this experiment resulted in a success. Okay. Okay. So let me say it this way. So let let AI be the event success on the ith trial. Okay, then A1 ... AN are independent, and hence so are, let me just say X1 equal to the indicator of A1 ... XN equal to the indicator of AN. Okay. And note that what is true about X in relationship to these? Well, it's just the sum of these things. X is equal to X1 plus X2 plus ... plus XN. Okay. And that's pretty nice, right? And now we're going to get really used to looking at these indicator variables, and it's going to be really simple to actually deal with this now. So watch this. Okay, so first of all, so note that what about this? What if I looked at the moment generating function of xi of t? Well, that's going to be the expected value of e to the t xi, which is, these are all indicator variables, right? So what's this going to be? You know, p, let me note that, let me just say p of ai. So that was the probability that we had success on the ith event. That's just p. Okay, so that means that xi is equal to 0 with probability 1 minus p, and it's equal to 1 with probability p. So this is going to be 1 minus p e to the t times 0 plus p times e to the t times 1. Okay, that's what the expected value, or that's what the expected value of e to the tx is. This is the moment generating function of this thing. So let me just say that this is just, right, we write this guy as q. So this is going to be q plus p e to the t. Okay. Now what? Well, okay, so what is the moment generating function of x? And this is something that we're going to start getting used to pretty soon. But look, we have a whole bunch of independent random variables that x is written as the sum of. So this is e to the tx, which by the way is expectation of e to the t x1 plus all the way through xn, which if I split this up, this is expectation of e to the t x1. I've done something like this before, txn, okay? And because I have independence, right, this is because of independence, the expectation of the product of these things is equal to the product of the expectations. So this is expectation e to the tx1, expectation e to the txn, okay? And each one of those has the same, and by the way, so this is like m x1 of t, m xn of t. And notice this right here is all gotten at because of independence. So whenever I have a sum of independent random variables, the moment generating function of that sum is equal to the product of the moment generating functions. Okay, so that's pretty cool. Should kind of remind you of the joint density, but there it was like the joint density of a random vector was equal to the product of the marginal densities. What's going on here is slightly different, but it's at least related. Okay, but look, I know what each one of these is equal to. It's equal to q plus p e to the t, and therefore, what do we get? You get the moment generating function q plus p e to the t all raised to the n power. Okay, we got that a different way before. We actually used the binomial theorem to pull that off, okay? We had to, look, I haven't even written down what the probability distribution function is for this. And I've already written down the moment generating function. That's amazing. I didn't have to even give you the PDF for this thing. And I'm able to write down the moment generating function. All I've told you is that the probability of AI is equal to P. That's it. And we're still able to write down the moment generating function. Okay, so that's amazing. Okay, so don't underestimate the power of writing a sum here. So X distributed as the binomial with n trials in proportion of success P has mx of t equal to q plus p e to the t raised to the n, and so let's kind of think about this for a minute, okay? Mx prime of t is equal to, what's that going to be? Well, np, okay, just the n comes down, so it's going to be q plus p e to the t raised to the n minus 1, okay? The power came down, decreased, but then I had to, oops, I'm missing something here. So should be p, sorry, there should be an e to the t in here. The derivative of the inside is p e to the t, okay? What about a second derivative? Okay, well, the second derivative is going to be what? Well, I'm gonna have to use the product rule. Okay, so it's going to be n minus 1, so it's the derivative of the first times the second, so it's going to be n minus 1 q plus p e to the t raised to the n minus 2 times p e to the t times e to the t plus, okay, so that was the derivative of the first times the second, plus the first, which is q plus p e to the t raised to the n minus 1 times the derivative of the second, okay? Oops, that's the second derivative. Okay, so let's just make sure we didn't make some kind of dumb mistake here. Yeah, so power comes down, decreases by 1 for the first derivative, and you have a p e to the t, and then you have to use the product rule for the second thing combined with the quotient rule, okay? So what happens here? We know that the expected value of x is equal to, now notice I have not written down a PDF at all at this point, but I'm going to be able to write down the expectation and the variance. That's what I'm saying, that having the moment generating function is just an incredibly powerful thing to have, okay? So the expectation of x is what? Well, it's mx prime of 0, okay? As we know, and what are we going to end up getting here? Well, it's going to be, if I plug in t equal to 0, e to the 0 is 1, so it's going to be q plus p, so it's np times q plus p to the n minus 1, but q plus p is 1. So it's np, okay? And what about the variance? Okay, well, that's the expected value of x squared minus the expected value of x squared, which is going to be m prime prime x of 0 minus mx prime of 0 squared. Okay, so what do we end up with here? Well, let's see. If I plug in 0 in for t into the second derivative, what am I going to get? np, okay, open parentheses. It looks to me like I'm going to get n minus 1 times p, because q plus p is 1 to the n minus 2. Okay, and then it's going to be plus 1. Okay, and then what are we going to end up getting here? So that's n minus, okay, so n minus 1 times p Okay, I think that's accurate. And then just that, yeah, so Q plus P. Okay, then it's going to be plus 1. Yeah, I think that's it. Okay, and then I have to subtract off NP squared, the square of that thing. Okay, so let's kind of sort this out here. What are we going to end up getting? Well, let's see. So let's see here. This guy right here is going to be NP minus P plus 1. Okay. Okay, so what are we going to get? If I distribute NP through, I'm going to have NP quantity squared minus, so minus NP, so it's going to be NP squared minus NP. Okay, so yeah, minus, well, okay, so right, minus NP times times P, okay, and then plus NP, okay, minus NP squared, okay. All right, so what is that? Well, that's just, these guys cancel, and you're just going to end up with, well, I mean, I kind of distributed that when I didn't really need to, I guess. I could factor out NP, and what's going to be left behind? 1 minus P. Okay, so that's going to be NP times 1 minus P, if you think about it for a second, which is just NPQ. Okay, so I have managed to find the mean and the variance without even knowing the distribution of the binomial random variable. All because I was willing to write X as a sum of indicator variables. So that's a powerful tool to have in our back pockets. Seeing a random variable as a sum of other random variables is very powerful. You basically reduces your computation to a much simpler problem. No doubt about it. Okay, as you can see right here, it seems like the derivatives are getting more and more complicated. And that's actually true. It turns out that there's going to be a technique we'll learn later on in chapter 7 that might help us out to that end, to where it's not going to be as complicated to necessarily find higher moments for this thing, okay? But that is to come. Indeed, later on, we will actually look at this indicator variable business more closely, and in particular, counting the number of events that occur and looking at that with great care, and looking at sums of those things. And eventually that will give us deep insight into how to compute higher moments of various random variables. And it turns out that factorial moments will come back to us. We've already talked about that in the context of the hypergeometric random variable. I've even mentioned factorial moments before. But we'll look at those with fresh eyes, just because I think it's really helpful to have that in your cognition. I think I'm going to stop right here for now. I wanted to talk a little bit about the hypergeometric random variable and something called the coupon collector problem, but I'm going to hold off on that. And then I'm going to pick and choose a couple of other topics from chapter 7, including what I just mentioned, namely talking about the number of events that occur and looking at that a little bit more deeply. Okay? Hope you all are doing well. Be sure to check in with me either during office hours or class time hours if you have any questions. Please don't hesitate to reach out. All right, that's all for now.